It's September 1975. America's automakers are in a full-blown engineering crisis. The Clean Air Act has just forced catalytic converters onto every new car. Horsepower is collapsing. Engines are being strangled with retarded timing, exhaust gas recirculation, and air injection systems that make cars stall at cruising speed. And right in the middle of that chaos, a team of engineers at General Motors files a patent for something remarkable. A system that can vary the lift of the intake valves while the engine is running. Not an exhaust after-treatment, not a band-aid. A solution that controls emissions at the source, inside the combustion chamber itself. GM tests it, GM patents it, and then GM kills it. 14 years later, a Honda engineer named Ikuo Kajitani builds the same fundamental idea into a 1.6-liter four-cylinder that produces 100 horsepower per liter and changes engine design forever. This is the story of how General Motors invented variable valve technology, abandoned it, and spent 30 years watching the rest of the world build the future it had filed away in a patent drawer. By 1975, Detroit was not designing engines. It was surviving regulations. The 1970 Clean Air Act had demanded a 90% reduction in tailpipe emissions, and Congress set that target knowing the technology to achieve it did not yet exist. The entire American auto industry pivoted to a single solution, the catalytic converter. General Motors and Ford sued the EPA to delay the 1975 deadline, then poured their research budgets into making converters work. Retarded spark timing killed power. Lean burn air injection caused stalling. Exhaust gas recirculation choked the engines further. But inside that collapsing research and development environment, someone at General Motors had a different idea. Instead of cleaning up exhaust after combustion, what if you controlled how the fuel-air charge entered the cylinder in the first place? The concept was variable valve lift. By minimizing valve lift at low engine loads, intake velocity stays high. Higher velocity means better atomization of the fuel charge. Better atomization means cleaner, more complete combustion, and that means fewer unburned hydrocarbons leaving the cylinder. The engineering logic was elegant. General Motors patented it in September 1975. And then they hit a wall. At very low lift settings, the system became unreliable. Airflow became erratic. The team could not solve the problem within the budget management was willing to fund because they had already committed to the catalytic converter. The converter was cheaper, faster to implement. It did not require redesigning the valve train of every engine in the lineup, so GM shelved the project. No production prototype, no development timeline, no champion willing to fight for it. The patent sat in a filing cabinet while GM bolted catalytic converters onto detuned V8s and watched horsepower fall for the next decade. While that patent gathered dust in Detroit, a young engineer at Honda's Tochigi Research and Development Center was about to solve the same problem GM had walked away from. Ikuo Kajitani joined Honda Research and Development in 1972 and spent the next decade learning where conventional engine design fell short. He worked on turbocharged engines, DOHC16 valve four-cylinder engines, and SOHC designs, and kept arriving at the same conclusion. The fundamental compromise in engine design was the camshaft. A cam profile optimized for low-speed torque sacrificed high RPM power. A profile tuned for high RPM performance made the engine rough and thirsty at low speed. Kajitani's insight was that you should not have to choose. In 1984, he began developing a mechanism that could switch between two completely different cam profiles while the engine was running. Honda's 1983 CBR 400F motorcycle had already proven the basic concept was sound. Kajitani's team designed a system using 3 cam lobes per pair of valves, totaling 24 lobes across the 16-valve, 4-cylinder. At low RPM, 2 outboard lobes operated the valves through individual rocker arms, and at a predetermined speed, oil pressure forced plungers to slide horizontally, locking all three rocker arms together. Now the valves followed the center lobe, a high lift, long-duration race profile. 2 engines in one block. The durability target was 400,000 switching events per rocker arm. His boss, Nobuhiko Kawamoto, pushed the performance target higher. The original spec called for 90 horsepower per liter. Kawamoto told Kajitani to aim for 100. No naturally aspirated production engine had ever achieved that number. In April 1989, the Honda B16A debuted in the Japanese market Integra XSI. It produced 160 horsepower from 1.6 liters at 7,600 RPM, 100 horsepower per liter. No turbocharger, no supercharger. For context, the Chevrolet Corvette's 5.7-liter V8 made 245 horsepower that same year. Honda was extracting more power per liter from a 4-cylinder economy engine than General Motors could get from its flagship sports car. The technology Honda called VTEC was the direct descendant of the idea General Motors had patented 14 years earlier and abandoned because it was too hard to finish. By 1991, VTEC powered the Acura NSX. By 2001, roughly 80% of all Honda engines used some version of the system, and General Motors was still running fixed camshafts. The rest of the industry did not wait. Alfa Romeo put variable valve timing into production in the 1980 Spider. BMW launched Vanos in 1992. Toyota introduced VVTY in the mid-1990s. Nissan had been developing its own NVCS system since 1986. By the new millennium, variable valve technology was no longer exotic. It was expected. GM did not put variable valve timing into a production engine until 2005, 30 years after filing the patent. The first applications were the LZE and LZ4 pushrod V6 engines using an electronically controlled hydraulic cam phaser. The following year, the Vortex 6200 became the first pushrod Vive 8 with variable valve timing, and the results proved exactly what the 1975 patent had predicted. Emissions dropped. The EGR valve became unnecessary. Fuel efficiency improved. The technology worked precisely the way GM's own engineers had theorized 3 decades earlier. The cost of that 30-year delay is difficult to overstate. While GM was bolting EGR valves and catalytic converters onto progressively weaker engines, Honda, Toyota, BMW, and Nissan were building the engineering reputation that would define the next generation of the global auto industry. Honda's VTEC became a cultural phenomenon. Toyota's VVTI became the quiet backbone of the world's best-selling car company. GM's contribution to that revolution was a patent from 1975 that nobody inside the company was willing to develop. So here is what GM's own engineers already knew in 1975. Controlling the combustion event at the valve is a fundamentally superior approach to cleaning up exhaust after the fact. Variable valve technology does not fight the engine. It makes the engine smarter. GM proved the concept on paper, proved it in testing, and proved it was worth patenting. What they did not prove was that it was worth fighting for inside a corporation that had already chosen the cheaper, faster path. Today, there is not a single major automaker on Earth that sells a gasoline engine without some form of variable valve timing. GM itself now uses it across its entire lineup. The technology they abandoned in the mid-1970s became the single most universal engine technology of the 21st century. That is not a failure of engineering. That is a failure of institutional courage. Thanks for watching. If this story hit the mark, drop a like and let me know in the comments. Here's the question I want you to argue about. If GM had committed to variable valve technology in 1975 instead of pouring everything into catalytic converters, would Honda's VTEC revolution have ever happened? Or would GM still own the future of engine design? Subscribe for more forgotten stories from American automotive history. I will see you in the next one.